Okay, we're going to talk about the type of objects, and that's really just like usually what we mean by the file extension. So, for example, um, we'll often use CSV file extension, comma separated value, um, or Weka usually, or the native, the so-called native data format for Weka is the ARF format. So I guess we'll have to um, go into exactly what that is. We haven't done that yet. Anyway, so that's what we'll mean by the type. The size of a data set, that's pretty clear. How big, how many megabytes, gigabytes, or terabytes. The dimensionality refers to the number of attributes in a data set. Um, Real-life data files vary significantly in dimensionality. A survey often has tens of dimensions for recording answers to the survey questions. A shopping transaction may well have over 100 dimensions if each dimension corresponds to a purchased item. So if you want to allow people to, you want to allow to be able to record up to 100 items that people may purchase at one time, then you'd need 100 dimensions. A digital image of 120 by 200 pixels can be considered as a record of 24,000, that is this times this, dimensions if the color value of each pixel needs to be recorded. So we have 120 by 200 pixels, and then suppose we want to take that file and record the color value for each of those pixels. So then we'd need 24,000 dimensions to do that. That would be each photograph or each image that is 120 by 200 pixels would be one object, and we'd record the color level for each pixel. So each of the 24,000 pixels. The dimensionality for a short digital video of tens or hundreds of frames is even higher. Data sets with very high dimensionality can make meaningful and effective data mining extremely difficult. This is known as the curse of dimensionality. Data can be very diverse, and therefore any patterns can be easily lost in a high dimension space. Computation for data analysis in high dimensional space can also be very costly in terms of computation speed and memory resources required. Okay, the next thing is sparsity. Data values collected in a real-life environment can be different from those collected in a controlled environment. The values may not be distributed normally or uniformly. Normally means according to the normal curve. Uniformly means kind of evenly. Often data values are skewed to a small number of diverse subranges. So you might find a lot. For example, if you're looking at people's income, you might find sort of a lot of data up maybe at very high income, and a lot at very low income, and a lot right in the middle. But outside of those areas, you might not find much. Actually, that's probably not true, but that's possible. Okay, just as an example anyway. So often data values are skewed to a small number of diverse subranges. Sparsity can be a challenge. So this is sparsity. Sparsity means the data, you have a big space, and the data only exists in sort of small regions of that space. Sparsity can be a challenge as well as an opportunity for data mining. On the one hand, it is difficult to see patterns in extremely skewed data, and some form of data transformation is often required to spread the data out. So you may have it sort of located in just these small regions. You want to sort of spread it out before patterns can be identified. On the other hand, the sparsity of data may speed up the discovery process if efforts are concentrated only on the subranges. Abstraction. Abstraction can be presented at different levels. Data can be presented at different levels of abstraction. At the least abstract level, data are presented as they are recorded. This is known as raw data. And the next thing you could do is you could summarize the raw data and approximate it. And that's one level up on this abstraction scale. For instance, in an analysis of student intake numbers over the years, so like APU might be interested in how many students came last year, how many students came the year before, how many students came the year before that, and so on. They're interested in the student intake over the years. Individual student record details are not really of interest in this study, right? We don't care whether how tall the student is or how much they weighed or whatever. We're just interested in the number in this particular question. So, but the total number of students each year is of interest. The latter value is summarized by query operations over the original data record. So you just do a sum, a total. Approximation of original data is another way of achieving data abstraction. For instance, a person's height may be measured in centimeters and then summarized as tall, medium, or short, right? So that's approximating. It's worth noting that at different abstraction levels, data properties may be different. In the previous example, a person's height is measured in a ratio scale. So, right, when you measure someone's height, that's ratio. It's even more than interval, right? It's ratio because 0 means 0. It means no height. Okay? But summarized on an ordinal scale, when we approximate it as tall, medium, or short, then when we summarize it that way, or approximate it that way, it becomes an ordinal scale. So it's worth noting that at different abstraction levels, data properties may be different. The different data properties may have an effect on the patterns to be mined. The level of data abstraction to be used is about the types of patterns to be mined, which in turn is determined by the intended purpose of discovery. So depending on, I guess what we're saying is, depending on what you're after in the discovery or in the data mining, you have to consider in what sense you want to do data abstraction. Okay.